Okay, thank you, Fernanda, for the invitation. Thank you for the introduction. Thank you, Jesper, for the very good background he gave us on sustainable products. I'm currently a freelancer, not with the Impact Energy anymore because I've retired, I'm sorry, a couple of years ago. And now you can reach me just by my own company. That's sort of what happens with elderly people. Gray hairs and long in the arena. And then I want to indicate also on the lower part this IEC and ISO Kaizen project, which I've been very hard working together with a couple of other people. Also, Jesper was there 2 years ago when we launched it, pretty much 2 years ago, precisely in Tokyo. And I will later come back to this topic. Today, I want to talk about efficient energy systems for a net zero emission world. And I will go forward. Let me see, like that. Doesn't work yet, but I will come. No, doesn't really work. Okay. Go back to share the screen again, I'm sorry. So now. Okay. Net zero 2050 is a fundamental challenge to our traditional energy system based on fossil energy supply. 2050 is less than 30 years from now. That's fast to change the entire industry. And in motor systems, we depend mainly on electricity. No fossil and nuclear energy will be available after a certain time. So, sorry. Now you have 3 possibilities to come down within the remaining 30 years to net zero. You can go in the usual way we have been discussing the last couple of years with the business as usual of a reduction rate of -1% per year through efficiency. You can, of course, also increase efficiency. Then you might come to 3%, 4%, 5% efficiency. If you want to go much further, then you're certainly invited to use renewables as the key driver for lowering your CO2 emissions. And if you really want to come to something like below 10%, I think you also have to reach out for the third possibility, which is the carbon capture and carbon capture at the end use site. That means if you're a company running a big business and emitting a lot of CO2 every year, these are the 3 major means, and the size of the 3 circles indicate maybe their relative importance. Now, there are 2 key global indicators that sort of follow through with what is going to happen. The first is the carbon intensity of the electricity delivered. If the electricity would be 0 carbon, no problem, but that's not the case. Actually, currently, we emit something like 450 grams per kilowatt hour. And when you look at the development in the last couple of years, since the year 2000, all these countries indicated here, from China, India, Germany, the European Union, the USA, and Canada, all have sort of followed a slightly inclined downward path to 415. But eventually we want to reach something like 100 or below 100. That means there's a long way to go, and certainly the inclination of the curve is not enough. The other very important indicator is decoupling. That means that we can have energy use depending on many things. I will come back to that. And at the same time have a GDP that is growing, but the total energy supply is not growing as much. In the last 30 years, you can see that the increase of the total energy supply is sort of not just horizontal, but getting a little bit flatter. and the increase of the GDP is increasing. That means we already see an effect in the global economy of decoupling. Now, industry will be the key sector. All branches of industry will need to be inventive. Efficiency is the joker card. It's about 50% savings for an entire company, or better, 70%. So far, the old goal of savings was something like 10%, or if you were a strong player, maybe 30%, and it was focused on some machine, not the entire factory. This is certainly not good enough for the future. Now, I want to explain why this net zero game, net zero goal, net zero drive is such an important thing for the global electrification between 2020 and 2050. On the left side, I have indicated the demand side of electricity use, and on the right side, the supply side. Now I've highlighted some elements that are increasing the CO2 emission. First and most important part is the electrification of many underdeveloped parts of the world, the rural area. This will increase the demand. Part of the still increasing curve of total energy supply is because of this. Then the second is, of course, that we are undergoing a heavy fuel switch. Heat, basically fossil, is now jumping to heat pumps. Electrical mobility is jumping to electric vehicles. This will certainly increase the demand for electricity. And then you also have the transformation in labor. Labor is being replaced by robotic machines. And on the lower right, on the supply side, certainly the heavy use of batteries, which have heavier losses, will increase the necessity for additional, will increase the emission of CO2. On the positive side, you have, of course, the whole efficiency complex with integrated machines, with heating, ventilation, air conditioning systems, with appliances, with lighting. This sector is certainly a bigger contributor to the lowering of CO2 emissions. Also, the addition of thermal power plants from the geothermal and biomass. You have to watch what you emit from the biomass, but geothermal, once you have found a proper situation, you can have a heavy contribution. And in the mechanical power plant, there's still the hope that the hydro, the wind, and the marine power can be increased over the next 30 years. Of course, also the electronic power plants, the photovoltaics, will be an addition to lowering the CO2 emission and to providing renewable electric energy. So you can see it's a mixed picture between the red ones that increase the CO2 emissions and the green ones that reduce it. And you can also see that the fossil power and the nuclear power will have to disappear before 2050. Now, I looked at some figures from the International Energy Agency that they presented in the context of their IEA's net zero program. And first view is on the electricity demand from now to 2050. Now, the interesting thing is this gray dotted curve starting at something over 22 petawatt hours per year increases until 2050 to something like 47 petawatt hours. This means the demand for electricity doubles, and it includes already all the savings. That means we have a very severe problem that the red points I just showed you on the last slide will be stronger in the increase than the savings and the reduction that I indicated with the green dots. Now, when you look at the same situation from the electricity supply side, you can see between 2020 and 2050, according to this IEA net zero scenario, you will have a total overturn of the current situation. This is still the dotted gray line for the demand. You can see an explosion almost, an 8-fold increase of the renewables, all kinds, solar, wind, biomass, all hydro. And you can see the decrease of the current fossil, and you can see the low and still unimportant role of nuclear remaining. That means we'll have a total change of the energy demand and supply system coming for the next 30 years. Now, this means for industrial motor systems, now coming down from the global to the meso level, where you have a big company, where products or industrial products are produced or services are delivered, then you have to think, what does that mean for us? What is this global goal for net zero meaning for us? I would say there are 5 points. The first is to reduce demand. Pressure in a motor system, that means pressure and flow, capacity, temperature. Many of those demands are actually not needed, but they're delivered. Many compressed air systems run at pressures that are actually not needed at all. Second, downsize all components. Our research shows that maybe 2/3 of all motor systems are oversized. Oversized for a state that never exists or never existed and might never exist in the future. Therefore, you can save on material costs when you downsize your systems to the actual need. Third, use the systems only when necessary. We still see lots of systems unnecessarily running at night, running over weekends, running during holidays and so on. Therefore, when you cut on the time according to the actual need, you can save a lot of energy. Fourth, today, thanks that Danfoss had the first speaker slot, load control is imperative, mostly for things that have a variation of the load, also for machines that have a very high starting situation and difficult stopping situation, but load control will become imperative. From our research, only 20% of systems have a load control, and easily 40, 50, even 60% in the future could have load control. And the fifth, go to direct drive wherever possible. Direct drive means the motor and the application is linked together directly. No gears, no intermediary transmissions. Now, your company can develop into 2 directions at the same time. It can go to efficiency first, because it's usually the cheapest, and it can on the same time also start with on-site renewables. I showed you in one of the first slides that we have 3 elements: efficiency, on-site renewables, and carbon capture. I would advise any company which is in a regular size to at least focus, on these 2 elements. I'm a little bit, okay. Then your company will design its own net zero plan. Today, they have usually a 1 or 2 year production plan, and they have maybe a 1 or 2 or 3 year plan that they can write nice sustainability reports each year and prove that they're really coming down a little bit. But I think every company of a size, let's say, with more than 1,000 people working, will need to have its own net zero plan for 2050. And of course, during this time, renewables are getting competitive in price, in availability, with grid electricity and with efficiency. That means you really have a lot of chances to do what you need to do. Now, I want to show you some efficient and inefficient systems. This car is the #1 gas guzzler I found in the US market today. It's a Range Rover, and it uses something like 130 kilowatt hours per 100 kilometer. And it is, of course, fossil fuel driven. Of course, you can also drive 5 people with the same kind of comfort, but with a little smaller car. And it can be electric driven, and it only uses 11.7 kilowatt hours per year. This is the most efficient electric cars I found on the market. Therefore, you have a choice. You have a choice. The same choice you have when you look at your fan systems. This is a typical fan system with a huge fan on the right side, and with a huge motor, and of course with the pulleys and transmission V-belts, I'm sure, and no indication that there is a load control. Therefore, there's a big increase possible for energy efficiency of every fan system I know. Same thing true for pumps. I have even, I would say, almost a historic system, but we found similar installations in Europe, in China, in many places that look like you found them in a museum, but they're still, this pump is under operation today. Same thing is true for air compressors. Here is a more modern system, which has already integrated cooling and heat use, but also here, the path to using the most efficient motors, to use load control for the motors, to use the most efficient available compressor types, and then to use only the pressure for the air you need, and the pressure you need if you have a cooling compressor, we are far away from having an optimum situation in the whole world. This is a typical example we found in our industry work. We found these three pretty heavy pumps, and we were surprised that they had so nicely new systems, good insulation, nice coloring. And then we looked at the rating plate. We found they were BBC. They were installed before 1988. They just had refurbished and painted them new, but they're unchanged. That means 12, 31, 21, that's something over 30 years. This is over the expected lifetime of such a system. And if you would replace this system, all the motors, and I'm sure all the pumps, you would make them lower, you would smaller, you would make the pump system more efficient, and you would drive them together in a variable speed control system. You would save plenty of energy. I will show you an example shortly. And this, of course, is the modern example. You have a ABB synchronous reluctance motor that reaches IE5. The last one was maybe reaching IE0 or maybe IE1. And you can see the looks of the motor have not changed very much. It still has a fan on the B side. It still has the pump on the A side. It still has these cooling ribs. And it has the switch box on top or on the side. And it has 4 feet and is mounted on a prop. In this case, it looks almost like it was downsized, and now you have to add a prop to bring the motor on the right size of the shaft. Typical after a renovation with energy efficiency and downsizing. Now, of course, also the variable frequency converter is now a standard tool. Many of the machines need it. And I think I don't have to explain you that this is a very valuable contribution. Don't forget that also a frequency converter has losses, especially in part load, and you have to adjust your calculations because it not only has a loss in the converter itself, but also it reduces the efficiency of the motor a little bit because it doesn't provide a perfect sinus curve. Now, I want to show you the number one case. It's a very generic case of what happens when you improve an existing system. On the outset, you have any 10 kilowatt nominal output machine. Could be a pump, a fan, anything that rotates. It starts with the machine being oversized, operating with fixed speed, has gears and V-belts, and it uses current components like motors and pumps and whatever. Can be improved, downsized, first thing, adjustable speed drive, direct drive, avoiding gears and belts, and using efficient components like state-of-the-art motors, variable frequency drives, and pumps and fans. Now, this is a sequence of efficiencies. This is the efficiency of the variable frequency converter, the motor, the gear, the belt, the pump, and then that's the consolidated efficiency. I've always indicated the full load efficiency and the part load efficiency. In the case of the VFC, old type, you have 92% in full load and maybe 75% in partial load because the machine runs frequently between 20 and 30% of the necessary load. That means torque and speed are reduced. In the motor, same thing, 90% if it runs full speed, 80% if it's running on average in lower speed. Gear is something like 95%, belt also 95%, and their respective partial efficiency are a little bit lower. And the big, if you want, increase can be made if you have a good pump. This is an old pump, 70% efficiency at nominal, but you're using it mostly in the 50% in the part load. Now, if you multiply the VFC, the motor, the gear, the belt, and the pump efficiency, you reach 52% on the full load and 25% efficiency on the part load. Now you start to work. You put in a smaller motor and VFC, you go to the highest available VFC quality. You carefully calculate when it is on the full load, when it's on the part load. You do the same thing with the motor. You avoid using a gear and the belt, therefore here is 100%, no losses. And you go to a pump which has 80%. You might change the type of pump, but you come to 80% and 70% in part load because it's properly sized and is not used under a situation where it cannot use its proper strength. And you see the average Nominal efficiency comes to 74. Before we had 52, and the average part load efficiency comes to 55. Now, what does it mean? In the existing system, you have been using 89,000 kilowatt hours per year, and the energy cost was 133,000 over a 10-year period with current electricity prices. In the new system, you use only 15,900 kilowatt hours, savings of 73, and you use only 23,800 for the energy cost, and you save 109,000. Together, what we have learned in this very generic, you can say very abstract example, which is typical for many kinds of machines of this size, 10 kilowatt, can be used for pumps, for fans, for compressors. The savings is even larger than 82%. And the energy cost savings are around 109,000 in 10 years. 10 years is more or less the nominal lifetime, expected lifetime of a 10 kilowatt machine. What you need to buy for this savings, you need to buy a half size 5 kilowatt IE4 motor, costs you something like €1,000. You have to buy a new 5 kilowatt IE3 VFC. IE3 is the highest available VFC class, not yet standardized, cost you 1,000, same thing as the motor. And you have to buy a new 5 kilowatt, whatever it is, pump or fan, costs you more, maybe 2,000 with all the respective adaptations. And you have the whole system get installed and adapted, measured before, measured after. That costs you maybe 4,000. Altogether, 1,000, 2,000, 4,000. You have 8,000. And that is only around 1 year payback. And I want to draw a very important conclusion. The conclusion is money is usually not the barrier. Usually the barrier to do that is on other things. And the economy of such an intensive replacement, the renewal of a system with downsizing and using best components, matched components, and direct drive, is the economy is usually no problem at all. Now, fundamental change means everybody has to get on board. Urgency means to start now. Make a plan for your company, your house, your mobility, set your priorities now. Electricity is made from renewable sources, day and night, summer and winter. That's what we are going to live through. Now, for the end, I want to show you this work I have indicated at the beginning, that we are coordinating, trying to coordinate IEC and ISO standards. In the case of IEC, is a responsible standard maker globally for all things electrical. In the case of ISO, is responsible globally for all things mechanical. Now, the direct path to better electric motor-driven systems is the coordination of standards. Systems need coordinated standards. Actually, 9 technical committees from IEC and ISO work on that. There is the TC121 in IEC for switchgear and control gear, the TC22 for adjustable speed drive, the IEC TC2 for rotating machinery, and on the mechanical side, there is the ISO TC41 for pulleys and belts, TC60 for gears, TC115 for pumps, TC117 for fans, TC86 for cooling compressors, and TC118 for air compressors. That means these 9 technical committees have to start working together, have to start agreeing on joint system standards, on standard for testing, from the input to the output, from the wire to the water, from the wire to the air. And now we are happy to announce that after 2 years of preparatory work, the launch of an IEC and ISO joint advisory group is imminent. The so-called JAC 22 will be launched on 20 October 21. I'm happy to announce that. That has been my ideas about going to net zero. Thank you for your attention. Maybe there are any questions.